Muchas gracias, Alejandro. Eh, well, I'm going to switch into English uh, because we have a friend here. So what I'm going to talk about today, and I'm very thankful to Alejandro, and it's always nice to be back to this place that I call home to. Even in 88, 89, I was a student, a helper of Dr. Silvia Torres. And what I learned from her was, if you don't know, don't say stupid things, just keep quiet. I think I haven't followed that advice very well. So so the nice thing is I learned the book the Osterbrook book from her on a one-to-one basis. So I was very privileged. And the other thing was that if she said that I wasn't a subject for a foreign PhD, I wasn't going to go. If in her evaluation, if she would say, Omar cannot go, he's not ready or whatever, I wouldn't have gone to Canada. So I'm very thankful that she did. Later she regretted, but it was too late. Well, now is so every time I come here, I always say thank you because my pass through my PhD was I got a recommendation letter from Manuel without knowing me, and then that was something that I'm very grateful. Okay, so I'm an observer, so you will not see many equations here. I will tell a story, and I only have one equation. I hope I wrote it right, and that's all that I will have on general relativity, and the rest is observational astronomy, and those are the limits. And what you call a black hole is not the same what we call a black hole, and we've been fighting for a long time. And it's basically at one point we only said it was a very compact object, and we didn't know the equation of state up to now with the LMT, that we can say that we have something that resembles very closely a, a rotating black hole, a Kerr black hole, right? So that's up here. Okay. So that's the only equation I have, Alejandro. So that's a very beautiful equation, actually. It was discovered by this guy who you know is Carl Schwarzschild. Carl wrote that equation in 1916. In 1916, things were a little bit how do you call it? The world was in big chaos. It was the First World War, and from actually he was in the front. He found that solution and sent it immediately to Einstein. Einstein reported to the Prussian Academy of Sciences, and that's an analytical solution found for a distribution of matter that is a point and is with a spherical symmetry. And then that's why you can see the coordinates there. And the only thing that I want to call the attention to, you should all know that there's nothing wrong when you reach the radius 2mg over c squared. It's just a border, but nothing special happens there. It's just on one side. You cross that boundary, and they will never learn anything about you. But some people said that was a singularity, that the singularity is not there. Many of you know that, but some people have told me that it took a while to realize that. And then if you do a change of coordinates, you will see that the singularity is in the center, right? So what is important is the Schwarzschild radius, and it's a very small quantity actually. For the sun, it should be 3 kilometers, so it should be inside the sun. And then when you go to higher masses, then you can have larger event horizons, but with the distances, we haven't been able to see until 2017, we saw something. But this is the very first reporter source that was considered a black hole is Cygnus X1. So it was discovered, the first source discovered with a satellite, and they were very creative with the names. So this is the constellation of Cygnus, and it's the source 1. And then here is that where the astronomers, humble and feeble astronomers, come in, because the guy who measured the mass of Cygnus X1 for the first time was an astronomer. It wasn't a guy who knew relativity. I'm sure that he didn't know relativity, but he knew how to measure applying Newtonian gravity and using binary stars. He learned how to measure the mass, and that was the first thing. And this was this guy, Tom Bolton, in Toronto, a nice guy. Well, all the students fear him because he had a problem with the thyroid. He was always like angry and things like that. But he was a nice guy. And so he was the one who measured with the telescope inside that dome. The big one is at less than 2 meters. Was the biggest in Canada for a time, and that was a building of the David Dunlop Observatory outside Toronto, and now it's full of houses there, and then they were all about to shut it down. But it was the people from some interested people that rescued the place as a historical place. And the family of the Dunlops who donated the money to build it, they said, if you sell that place, we want the money back. And it was, 3 generations afterwards, and said, we want our money because you don't, that's our grandpa and whatever. So Tom Bolton they shut it down. It wasn't part of a university. It isn't part of a university. And the guy who is here in the front, that little guy, right there, that is Ian Shelton. Ian Shelton is saw by the naked eye in 1987, the last supernovae in the Magellanic Clouds. And now they say that there is a controversy now, but that's the guy. Ian wasn't able to enter the university because he didn't have good grades. But after he discovered the supernovae, he was admitted. I mean, the first guy in 300 years who saw supernovas. So what was it? Okay, so the history. The only place that you can measure stars around a black hole is our galaxy. And those are the 3 guys. Well, the 2 guys are the observers. And the guy in the middle is Reinhard Genzel. And Andrea Ghez. Genzel is from Germany. Andrea Ghez is from the United States. And what I want to call the attention is to the observation in the middle. It's over 30 years of observation following the star inside its orbit. And the thing is, every so many years, they change instruments. They upgrade the observations. They get a bigger telescope. They get more sensitive instrumentation. So they got these kind of observations. And what I feel jealous is that we cannot do something like that. CONACYT will give us money to run a 30-year project. That would be something that would be nice to do. And you have Sagittarius A star, and that is the position of a black hole. There is a shadow now of that. And you see, you can apply Kepler's law to learn about this thing. So these are the closest that you can approach to a black hole and get the orbits of the stars and measure what is the mass of the enclose the orbit. And that's one direct method to measure. And now we have a shadow of it. And then there is Roger Penrose that you all should know. Roger, if I don't know, if Hawking had survived, I don't know if it was him or Stephen who would be there as a theoretician. But Roger devised many theorems on black holes. And among the contributors to the theory of black holes is Subrahmanyan Chandrasekhar. In his late years, he entered the field and he did wonderful contributions, amazing contributions from a guy who had done classical physics for all the time. In his later years, he did great contributions. So, but Penrose is a guy who's always been there. And these are classical ways to measure using gas or matter, the masses of black holes. And this is the closest we have got. This is LIGO. This is something totally amazing. I mean, I thought that in my lifetime, I wasn't going to see this, a result from this experiment. Another 30 years, more than 30 years, 25 years with non-detections. 25 years that they would just, moving things. And then they dare to ask for more money. They said, like, we haven't got anything, but, if you give us more money, now we're going to get it. And they managed, actually. They gave them more money. They did an upgrade. This is a 4-kilometer arm of Michelson interferometer. And the great thing there is that it's a vacuum tube, a 4-kilometer vacuum tube, and a very, very powerful laser. And that thing consumes, like a small town in electricity. So one of the major contributors to this is the Department of Energy in the United States. And in 1914, they did the first detection ever. And they thought it was, a test, because what they were doing is they were injecting a signal to see if everybody was watching and things like that. And they did exactly what was expecting, this chirp. And it means when the black holes are coming together and they begin to coalesce, and then they rotate about each other and they merge. And that is exactly the signal that you expect. The theory is in the middle, the data is on top. And that was very, very impressive. I mean, it's to build 2 of these instruments, last for 25 years, waiting to tune up the experiment, and then getting a detection. That was amazing. But the Nobel Prize wasn't awarded until we saw one source. If they continue like that, nobody was going to believe them until the astronomers came and found a counterpart. And this is also something that many of you guys, or some of you guys, are working on, trying to construct the shadow of a black hole, assuming different metrics. And it was done by hand many years before computers. That one in the middle, in the top, that was done by hand after some calculations. It was Luminet, I think. And everybody ignored Luminet, but for the longest time, that was the only simulation of a shadow. And what you see is in the sketch below is the parts from behind are projected to the front through the gravitational lens that the black hole is doing. And due to the proximity, what you're going to see is like a mushroom type of thing, right? And well, this is a whole telescope. Again, is interferometry, the technique. And if you don't know anything about interferometry, it's time for you to learn something about it, because that's the only way that we're going to go higher in the dimensions, but the physical principle will be interferometry of light. And then now we have a telescope of the size of the Earth, because the resolution is defined by the maximum separation between the antennas. And that's what it gives you. It's almost like magic. You can construct a telescope of the size of Earth with a resolution, like if it were a continuous thing, but your sampling is really bad. Because what you need more points inside that circle to have better sampling. And if you begin to take out telescopes, nothing would happen. It's the same thing when you put your hand inside the mirror of a telescope. Your hand doesn't come. You're just blocking some light, and then the light goes around you, and then you did the things. So what you need to do to get a better image is put more telescopes. And if you put one antenna in space, for instance, then your resolution will be marvelous. And then if you can think about the solar system as putting telescopes anywhere, you will see the thing. So the way to do this is that you do a simulation, and then you go backwards, distorting the image according to, with the telescope and according with the noise, and your best recipe for the reconstruction of an image, and that's what you get on top, right? And they say there is a prediction that in 2029, and all the black holes look the same. They all are orange. I don't know why they picked those colors, but the one in our galaxy was orange. Oh, this is M87. It was orange. The one in our galaxy is also orange. So in 2029, with better resolution, I think it will be like a donut type of thing, right? But this is incredible thing. This is amazing. Pluto and the Voyager are inside the shadow of M87. So now we're talking about big, right? So this is 10 to the 9th solar masses, and the event horizon can fit inside the shadow. The event horizon is pointed over there. So it's bigger than our solar system. However, and this is, I'm going to leave it to you here. How come, if you have a structure that could be as big as the solar system, how come the rest of the galaxies knows about its black hole? How come there are relationships that I'm going to show you that, a very small region, this is the solar system, and the size of the solar system with a larger mass, and then you have the rest of the galaxies that are kiloparsecs apart, and there are correlations between these two things. That is something that we haven't answered yet, and it's beyond our standard models. So how big can a black hole grow, a supermassive black hole? So there are many recipes. Not that many. It's only one recipe. It's cold dark matter. And with cold dark matter, what you need to put is a seed of a black hole, and then allow for other black holes to merge and form a larger galaxy and a larger black hole. And so the biggest, according to the current paradigm, is 10 to the 10. We cannot build bigger than 10 to the 10. But this is going the opposite. We have a limit, the observational limit, that is 10 to the 10. And then you can work out the merger rates and all these things. And then you go and build something that resembles a mass of 10 to the 10. But you need to begin with something smaller. So if you want, your seed should be about 10 to the 4 to reach 10 to the 10 and the present. So this is more or less, the one that has more physics, I think, is Andrew King in terms of accretion. And there's no general relativity here, Alejandro. It's just plain cold dark matter, getting small balls and pelotitas, right? And putting them together. And there is a recipe. And I think here, and there is another limit that says we can reach 10 to the 11 solar masses. And that for me is just, blows my mind. I cannot accept something that should be a black hole with the mass of our whole galaxy. Theoretically, there's no limit. I asked Igor Novikov once and said, is there a limit for the growth of a black hole? We said, no, currently with general relativity, plain general relativity, it can grow as big as it can. And then last time I was in the Simba staff, there was a guy who wrote an article along with Novikov. This was Vladimir Manko, I think, from Simba staff, who said, I wrote a paper with him and said, you can build, there's no limit, is what he said. And then if you go and you push these ideas to the limit, the whole universe is a black hole. in terms of you can identify a horizon and then say that we cannot communicate or know about beyond that horizon, right? But that is just, when you get something, some good grass like the one the Pope smokes or something like that. So the limit is over here. They have looked thousands of galaxies with scaling laws, and it seems that 10 to the 10 is the limit that we have so far. But we're limited because of resolution. Because with the event horizon, we cannot go that far, right? And very massive objects are very rare. They are the beyond the knee of a Schechter function. So you just get a drop directly when you have M star, and then you go directly when you have the luminosity function. So the biggest objects are very rare. And so it will be rare to find big ones. So here, well, today, what are you? Emmanuel Rios López is the one who generated this plot. This is in a paper that has been accepted by monthly notices that we haven't been able to pay yet because we don't have money. We got a fee waiver of 30%. Emmanuel got another, and then perhaps I'm going to sell a kidney to pay the rest of the paper. But what you have there is, in this first graph, you have the logarithm of the velocity dispersion. This is the global velocity dispersion of a bulge, if you like, and in a spiral galaxy. And the red points you see, they follow a very narrow correlation. And that's one of the best. So what it says that if you measure the velocity dispersion, you can know the mass of a black hole. You can get an estimate. Or if you know the total luminosity, well, this is a defective radius. And the points in blue are bulges that are not classical bulges, but pseudo bulges. So that is on the smaller galaxies. You don't get a very round bulge. You can get a peanut-shaped type of thing. That is it's said that is an extension of the disk, and they seem to follow a different law. So it means that perhaps the galaxy has not reached equilibrium, so you get some dispersion. But in general, if you take away the fit to only the blue points, they don't go far away from the red ones. So not too far. And those are the one sigma errors. And what we did is that we got a sample of galaxies with measured masses, and then we measured the bulge doing surface dryness, the composition, and those are the results. So these are refinements to the previous correlations that we have found. And this is only light. So this is a little more dispersed, but using all the light of the galaxy, all the luminosity, counting all the stars and integrating the light, you get a correlation too. Why? We don't know why. There's no theory that says even cold dark matter cannot get that thing. I mean, you can build it and restrict it and say, you force the thing and you can get something like that. But the only thing that I can see here is that it's not even the size of your fingernail. This is like the size of ADN and the rest of it in comparison for in our bodies. And this ADN has all the information to build a copy of ourselves. So this thing is that the black hole defines the rest of the galaxy. And that is one way. So in 2012, Postman et al. Published a nice result with a galaxy at redshift 0.22. And what they found, they were for the longest time, the owners of all the HST time to do black holes. And this was a collaboration with Sandy Faber. Some of you might know her. Scott Tremaine, Howard, all these people, the nuclear guys, and they found this galaxy. And what they found, what was very interesting, was a very diffuse distribution of light in the center. And when you run the profile of the surface brightness, you found a large flattening in the inside. And that is due, supposedly, and then now with numerical simulations, they have shown that you have a binary black hole, supermassive binary black holes merging, and as they merge, they disperse the stars. And then they finally coalesce. And then that is what the leftover of having a large black hole. And there is a correlation, we can do correlation with whatever, and there is a correlation of the size of that flattening and the mass of the black hole. There is another correlation with the light that is missing here and the mass of the black hole. I mean, if you do an extrapolation of this profile, it will, all this light that was dispersed, also there is a correlation there. And you can put anything. I mean, the day you got your first date or whatever, and correlate it with the mass of the black hole, something might come out. So the feed to the light distribution, that is a nuclear profile, the one in red, and it has 3 slopes, one critical radius that is RB, and with that, the only thing that you wanted to get was the flattening. There's nothing, there's nothing physical. It's just something that, a function that would allow you to measure how flat these things and where is the break. That's all. It's not a fit to the whole galaxy either. It's just a way to measure the flattening, and that's it, right? And that is called the nuclear profile. It turned out that this profile is very fundamental at the end, because the Sersic profile is a special case of this profile. It was shown. And the Vacuolar's profile is a special case of the Sersic one. And the exponential disk, the feed that you use to feed the disk in galaxies, is a special case of the Vacuolar's. And then you can go even to the exponential. you can get there. So this is a very general function. And it turned out later, but it was looked only as a phenomenological interpretation of the observations. And then what you have here is R gamma. R gamma is an special radius. It can be, when you feed the nuclear profile, you can get R gamma as a function of gamma, beta, and alpha. And that's the analytical expression, or you can measure it non-parametrically. Is when in the profile you reach the slope of -1/2, and you can do it that way. So R gamma is preferred because the signal to noise is bigger, and that's the only thing. But it depends on R beta, RB, which is the break radius. So all the galaxies that this collaboration had measured are in blue. No, I mean in red, in blue. In blue are the ones with the flattening, and then 2261, ABL 2261 was breaking a record there, very high in this correlation. So that was good, but then the Mexicans came in. I had observed in 1993 a big galaxy. These are the brightest dominating galaxies in clusters. You cannot find them in the field. So I had another example that I have observed in 1993. It was odd because it showed that it was very diffuse in the center. But we didn't have measured. The nuclear profile was invented later. And the other thing is that the estimation for the mass of a black hole in this big galaxy in 2291 is 6 times to the 9 or 4 10 to the 10. That was what was inferred from the correlations. though at the time, only a few galaxies had been measured with masses around 10 to the 10. So that's the one. It's called Salute. Holm 15.8 for Holmberg is a catalog of binary galaxies. This was the cluster was not known. It was discovered later. It was in ABL 85, and that is the galaxy. And it's at low redshift at 0.05. The other one was at 0.2, and that's why they use HST. But with something at redshift of 0.05, you can use a small telescope, and that's what we had at the time. And also, it came at the right time because the first student I graduated as a PhD was Christopher Añorbe, and in his PhD, he developed a technique to do multiple fits to galaxies, a driver for a very common software that is called GalFit. And then there are other drivers, but this is ours. Our version is called DGCG. And then some theses have been worked with this. So on top, you have the 0.9 meter telescope with a seeing. If you would laugh about that seeing, is 1.6. It's worse than San Pedro Martyr, because San Pedro Martyr you can get better seeing, and even Cananea. We had reached sub-second seeing in Cananea. This was Kitt Peak, but it was 93, as I tell you, and it was dome seeing. What it's saying is in the dome wasn't ventilated properly, then you degraded the image just because of you were observing improperly. But there was 1.6, so people don't believe that you can do blood holes with 1.6 our second resolution. And the one in below is the CFHT, a 3.5 meter telescope with a seeing of about 0.7. And that was it, the same thing. So, yes, this is a commercial. Before we, the commercial is that we have some victims during the summers in Tonantzintla that is called Galaxy Maquila, because the Maquila doesn't require qualified people to do it, right? The Maquila doesn't need educated people to go and work in a maquiladora. You only have to do a repetitive thing many times. So what can you do with undergraduates who don't know anything about astronomy? So you get them into a maquila type of thing. And we were having a lot of fun during this time. And they have written papers, actually, after staying with us, suffering us for a summer, or we suffering them for a summer. So what we have is we divided by projects. So we give them GalFit, and now we have tools to plot the output of GalFit, that you have to do it with other facilities. Now you do it with them. You get the results from GalFit, and then you can immediately graph them, and you know those are publication quality, and that was done by Christopher Añorbe. And then you have kids, once they get their thing together, they are accepted to the Congreso Nacional de Física, and they send their posters. For a time, the guys from the UAP, Benemérita Universidad Autónoma de Puebla, if they got accepted, their poster was accepted, the UAP would pay them until last year. Now they make a selection. But our guys, well, we los apantallamos. So, and even some of these guys have been given talks at the national meeting. And that happened only once, but I had to go there to defend them. But and then we visit LMT and we have a lot of fun. So what we do is this last year, we did Virgo, most of the galaxies in Virgo. This year, we're going to do Coma. We are going to compare Virgo and Coma with these fits that are guided one by one with a human computer, an organic computer, right? So, all right, that was a commercial. we come back to home 15A. Then there you have it. That's the profile. It's not very flat. It's very long flat. But the break radius is at 1848 kiloparsecs. And the break radius is at 4.57 kiloparsecs, H-naught of 75. The same profile that the nuclear fit in 2 dimensions. We use most of the information on the galaxy. We don't do isophotos, we do areas on the galaxy. And that's what we got. And that was, up to now, the hardest paper to be accepted, published by our group. And it was led by me. And the thing is, there were 2 competing teams. It was the nuclear guys, and it was the Australian guys. And then the Mexicans came in the middle, and nobody knew us. And then these 2 guys turned and attacked us. So it was hard for the paper to be accepted. And finally, we convinced the editor, and it was accepted. And, well, the controversy came. But Home 15A was larger than the largest one done with HST. And done with a small telescope. But as I told you, the break radius is 18 kiloparsecs. It's about here. It's more than 10 arc seconds over here. The seeing disk is about here. So that doesn't affect much over here. And that is something that people don't understand. They say, no, you don't have the resolution to resolve this. Of course, if you have a break radius that is so far, you have the resolution. There's no problem about it. And then R gamma, well, that is a derived quantity from RB. So even when the seeing doesn't allow you to see R gamma, you can deduce R gamma from the fit. And that's what I told you, this previous scaling laws with Meson light, with excess light, with velocity dispersion, with light, the whole luminosity of the galaxy, with the break radius, and that's R gamma against black hole mass. There is another correlation there, not as good. R gamma, as I told you, is inside the flattening. What is the radius with a slope of -1/2. So nothing has been measured which is that as large as what we can measure. It's up to 1,000 is the record. So that was the mass that we derived, 2.1 10 to the 9, using M sigma. 9.2 10 to the 9, using the luminosity of the whole galaxy in the K band. The deficit of light is the light that is missing in the middle, gave us 2.6 10 to the 11. And that's when the thing began to get tricky. Hector was a student at INAOE. He's a co-author of this paper. And I went to tell him, we're getting 10 to the 11, Hector. So if you do it with RB, the break radius is 9 times 10 to the 10. And if you do R gamma, it's 3.1 10 to the 11. And of course, because not a lot of black holes, there was only one black hole measured with the mass higher than 10 to the 10. That was one of the galaxies in coma. We decided to say, we don't know, because extrapolating is the most difficult thing that you can do. I could have taken the average of these measurements, of these predictions, and get something that was close to 10 to the 11, but we said is 10 to the 10, and we left it like that. And we didn't were attacked by that prediction. We were attacked because of the flattening. And then the guys came with, it was Bonfini who was a postdoc at IRIA, I think. We got a fight sometimes. Well, he contacted me and said, I'm not getting your result. It was very weird because he got his own analysis. And then, of course, I wasn't going to get mad. If I was wrong, well, I was wrong. Yeah, I said, I'm not going to lose the knee for that. And only get a bad reputation. That's it. But he was very apologetic about it, saying, "Oh, well, I'm not getting it." Of course, he was using a more complicated profile that tried to fit the whole galaxy, but it didn't work for this galaxy. So what they say is there's no core, there's no flattening. And then this is what I said before at Simvestab, and I tell it to you again, be careful with whom you share your data with, because we share our data, and that has been the source of much grief, because we share the data with some colleagues from Argentina, and they use our data to attack us and say that there was no core because they fit the same profile, but not in the logarithmic form, and then they say this goes like that, so it's cuspy. And in the portal of Gemini, because they use observation, very noisy observations from Gemini, they say the supermassive black hole that wasn't. We didn't take it personally. I didn't write to them. I didn't say anything. I just said, well, there's no bad propaganda. There's no, who's this? Pardon, sorry. I mean, if they talk about you, that's good. so even if they say bad things. So I'm going next week to present the results that I'm going to present today here to show them. We also got data from GTC, and then Emmanuel was a proposal that he wrote. We got the spectra from Home 15A, and for another source that was nearby, the one with the circle, which was detected by Sloan. And they say that he had a photometric redshift. So we got a redshift for that because we thought it was a third black hole, because we ended having a coincidence in the line of near to the center of the core of our galaxy. Well, we thought there was a third one, but Emmanuel found that it was a quasar at higher redshift. There you have it. And lesson number 2, every time you get a result, publish it. We didn't publish, and then another Argentinian guy published. Got the data, not even say thank you or anything. It was when he didn't have to, but got the data from our proposal because it's published, and that happened with the biggest telescopes. You have 1 year of property, and then unless you ask for more, and then we didn't. We got it. Manuel got a prize for the best poster. Dario, you were there. The best poster that we had in the Congreso Nacional was Manuel's presenting the redshift of that. That's the only memoir that we have already analyzed the data. And then there's a guy whose initials are Madrid, who published both data. And then we have the VLA also with Mark Birkinshaw, the late Mark Birkinshaw. What we wanted to see was the presence of a double nuclei to say that we have emerging ongoing, but we didn't see anything with this high resolution. We are going to go VLBI to do it, to give it another try. And this is in the borderline for the resolution of a present Event Horizon Telescope. So we cannot do it yet. But we have gone with GTC and VLA observations. And these are simulations that you get the flattening if you include 2 black holes in 2 galaxies with black holes and they merge. And at the end of emerging, you get these flat profiles. So we were going in our happy lives, and then suddenly these guys, totally independently from us, got a direct measurement using Muse. We have data from Muse. It was you, Irene, the one who told me that there was data on this galaxy available. And they measure a mass of 4 times 10 to the 10 solar masses. And that became the biggest black hole ever measured. Not the ones, I mean, that it would be the biggest mass that you will ever detect, but this was the one that had been measured in Home 15A. And the data is available. And so you can analyze this. They did the profile and they got a full coincidence with us, even with the non-parametric ones. It was very nice up to the precision that we have reached. They got it, and we were very happy with that. And you can compare the evolution of emergence. And if you analyze the 2D data, you can infer the stage of evolution on the emergent type of thing. Okay, so this is where we began the counterattack. There is an image, public now, from Subaru Supreme camera with a scene of 0.78. It's very deep. It has exquisite resolution, the best that you can do from the ground. And that image was already processed by Mireia Montes. And we called her, she gave us the image, she gave us the mask, and we did the fit. She also tried to do the fit because she's interested on the color gradients in this type of galaxies. Because the idea is that the 2 big galaxies or 3 big galaxies merge, and then the rest of the light that can go up to a megaparsec is just destroy galaxies inside the cluster. And she's very interested in that. We are interested in the big one for this time. So using that data, this is Chris Añorbe's fit, and we recover our result. So this is the beginning of our strike back on these guys, and I'm going to present this to the Argentinians in their house. I'm going to go. I'm sorry if they don't invite me for an asado or whatever. And we have great instrumentation in our hand. This is Megara at the GTC. It's a superb instrument. Well, the spatial resolution is not as good, but the spectral resolution is superb. So we have combined and this sector work analyzing 2 resolutions or 2 different instruments and try to combine them to combine the best of the 2 observations: the spectral resolution of Megara and the spatial resolution of the BLT. And what is the name of the instrument at BLT? Is Muse, exactly. So this is the footprint of Megara. We got 5 hours. This was your proposal, Emmanuel, too, right? And one of the intermediate results that this was done by Hector on a single author paper. He removed all the galaxies, the cluster galaxies. You can remove that because you have the redshift of each galaxy. But he removed them, and then he got the ones marked by squares there are the galaxies behind, and he measured the strength of the gravitational lens at that very small region. So he got a constraint from observations from behind, using the tracers behind the black hole. Of course, it's not going like very, very close, but he got an enclosed mass of 10 to the 10. So that was, I was telling you that it was a good measurement. And then this is now the revolution in the sense that you can do stellar synthesis modeling, and you can believe actually the synthesis. When I met Gustavo Brizual in 1992, I was switching from stars into galaxies. Gustavo used to feed every single population with solar type stars. And I, who knew stars that had different metallicities out of classifying them, told him, right, this is a bit dangerous to do this, Dr. Brusual. And I was a young kid. And Gustavo said, that's what I have at hand. Only full traces for solar mass, solar metallicity. And you can do on a spiral and elliptical with these templates. But now you have templates of different metallicity, different ages. You can add dust, and you can get a decomposition when you get the integrated spectrum, and try to infer metallicity, age, and evolution of the stellar populations inside the galaxy. And this is something really, really amazing. Because on this side, you go to the galaxies at redshift 2, or around there in the middle, and even beyond, and measure the star formation rate directly using indicators of star formation rate. And on this side, you take a galaxy, a nearby galaxy, and do the reconstruction. And you go behind, you go backwards using this. This is the archaeological record now. And then you get the same cosmic noon is called now, I think, when you get the maximum star formation. So inside our galaxy or galaxies like us, you can reconstruct the history of star formation and tell the same history when you do use the tracers of galaxies at the epoch when they are having the biggest star formation burst. And that is very good. So we can believe this kind of analysis, but for the longest time, it was only looked as it was a curiosity in the sense that, oh, it's very, very nice, but it depends on what is your library, what is your minimization record and all these things. But now we can get beautiful things as this. This is the velocity dispersion. The running the velocity, but this is your sector. On Muse data is very flat. So he's suggesting if Javier was here, he had a model where you get 3-body heating to produce this flattening and get it to survive. So this is indirectly is suggesting that there is a third body there that is helping with the dispersion and you see the flattening is over here. It's the same in light. So that's a very nice result that we need to look at. The stellar mass, well, you go in radius, you're enclosing more mass. And this is the age. It's very well mixed. 5 minutes. Yeah, I'm almost done. Very well mixed. So the black holes are like a blender. And this is the workings of dynamical friction. That the way I see it is you have a black hole, it creates an overdensity behind, and it's like a parachute when you have an airplane. So you get an overdensity behind the black hole because it's dispersing the stars, and then it goes and it loses velocity and merges in the middle. That is more or less the story. The metallicity, we can do also the metallicity, and it's comparable with the R gamma is where you have 1 there, 10 to the 0. Is a very flat metallicity gradient measured directly now, or with models. Okay, I'm going to go very fast here. Well, from simulations, you can get now the contributions of the stars into the big galaxy from the other galaxies and from the galaxy itself. And what it says here in these results from Montenegro Taborda, from IRIA, is that most of the light is coming from ex situ is means that is contributed by other galaxies, not the galaxy in the center. We have to talk about this, Alejandro, the jet and then the gas, and we have a biggest resolution. We are going to get more maps for this. Home 15A is the largest core ever measured. Well, I don't want you to read that thing, but this is from Rio López. There are more candidates, around 10 to the 10. All the ones that you see 10 in this M black hole mass, whatever you read that is 10, this is a good candidate. Okay, black holes everywhere. I'm reviving this project, and I'm getting for victims or come and save the country. Black holes are everywhere. And nobody said that they could be at the beginning of the cosmic dawn. Or you have to get them somehow. And if they contribute to the accretion method, accretion power, they radiate ultraviolet radiation, and they can ionize H1 or excited, and then you can get this is the spectrum that you expect from 21 centimeters, the line excited by different methods, by different epochs of star formation. So around redshift 20, there is a big explosion of stars that it manifests as an absorption here. So if you detect that, you know the epoch of it's a very clean observation, very hard to do though. And we have an experiment, it's called, is that the way we put it? Sonda Cosmológica de las Islas para la detección de hidrógeno neutro. And it's pronounced Sci-Hi, so the Americans can read it. So, and we're called in the literature that way. You cannot do this experiment anywhere in the United States but Mexico, and Zona del Silencio, in Chihuahua, Coahuila, and what is it, the other one, Durango, or Cataviñá, Desierto Central, Baja California, and Isla Guadalupe. So we done our experiments, we have been measuring, trying to identify the best radio quiet places in Mexico. That is Cataviña. We were there in 2021. And this is Isla Guadalupe. The one in red in that side is Greenbanks. It's a radio quiet force zone in the United States. It doesn't work. Look at all those jumps are radio stations. And experiment. This is the first result. We need to improve, but we gave a proof of concept because the main contributor to this signal is our FM. La comadre over here is very powerful. So that is the first result. Tan tan. Thank you. Oh, the pizza is getting cold.
Pizza, in the meantime, we can ask questions, please.
Okay, leave me a slide. No, it's fine. ¿Ya regresaste, Darío? Yo te hacía todo en Portugal.
No, hombre, ya quedé de comida y clima portugués hasta el cepillo.
Ya no quieres nada. Ya. Tenemos a Darío.
Sí. De hecho, muy amable Alejandro me manda los links de la charla, pero no había podido venir y dije, no, pues a los
Todos están interesados.
Sí,
No, pues, muchas gracias. Pues
los
te digo,
que están quitando informativo.
no, ¿te la pelaron? ¿Te la
Ahora
pelaron?
sí te quisieron interpelar.
Pero pues se la pelaron. Pero ahora sí les voy a dar una, o sea, con la mejor resolución lo recuperamos. O sea, ahí está. Es más, ya les llaman, ya los australianos le pusieron un nombre especial. Se llaman overmerge. ¿No?
Interesante.
Porque ya tiene un agujero de 4 por 10 a la 10, o sea, ¿cómo lo vas a quitar? 4, sí. O sea, si no tiene el flattening ahí, pues entonces tiene que cambiar todo el paradigma. Entonces lo que quiere decir es que este es uno que ha aplanado mucho, ¿no?
Está muy interesante. Bueno,
Es
pues,
especial.
¿cómo estás tú?
Muy bien.
Ya quita tu micrófono.
No, pero va a haber preguntas. Ya le cortamos a la.
¿Ahorita va a haber preguntas o
Creo que sí. Sí va a haber preguntas, ¿no?
por qué ellos separaron todo?
Porque se va a enfriar la pizza.
Ah, fueron por la...
Ahí está.
¿Qué masa tendrían los otros agujeros más a Z20, más o menos?
No serían muy grandes. 10 a la
La-
4 por 10 a las 5. 4 con 10.
10 a la 4,
10 a la 4 de 10,000 a 100,000.
Bueno, además vengo, ya me tengo que ir ahorita rápido, tengo que recoger a los niños de la escuela.
Órale.
Me dijo Alejandro que van a comer en la tarde.
En la tarde vamos a ir a unos tacos por ahí.
Ah, ok, entonces
Según-
ahí nos alcanza. ¿No? Mensaje
Ahí le
está.
pasa, sí,
Ya,
te
ya,
lo pasamos, sí. Sí, sí, con gusto.
¿Cómo estás tú? ¿Cómo va todo?
Todo bien, bueno, pues, ahora sí le vamos a cortar aquí. Eso.
¿Cómo va todo ahí? Cuenta, cuenta.
No, que los tienen, un montón de recortes, ¿no?
Bueno, eso sí, como todos.
Ustedes tienen suerte por la autonomía, ¿no?
Sí.
Pero nosotros no. Nosotros dependemos directamente de la Secretaría.
Vamos con el micrófono así.
Sí.
In Zoom, do you have questions? Or here, who wants to start? Rita, you understood everything?
Sí, para que se calmen, ¿no? Si ya estaban enojados.
Okay,
No.
questions?
No tienen ustedes preguntas, yo tengo preguntas.
Yes, I was wondering about the black hole masses about redshift 20, the one you say at the end.
10 to the 4.
Entonces, no soy el caso de black hole sí. I mean, está un tiempo to look for the black hole.
They have been finding every time more 10 to the 5, a redshift. What is it? 3, 4, 5, 9. So it's getting there. But in this place, I mean, it would be inferred indirectly in the spectrum when once we get a clean detection of the spectrum. In 2018, ECHES, a collaboration, also a single antenna experiment, said in Nature that they had detected the signal, and it was huge. And everybody called me and said, "Oh, you missed oh, these guys." I mean, they were laughing at me because they said that we were not going to get it. But it happened that that result was spurious. It is mostly, it has been reported recently, that is a signal in our ionosphere, what they saw, not the cosmic signal. It resembles that result from BICEP, if you remember, that it was dust from our galaxy instead of cosmic dust. So now everybody's being very careful. So we are trying to reach the other islands in the Pacific, in archipelago de Revillagigedo, to have more antennas in very radio quiet places and try to do observations simultaneously or coordinated at least in order to separate the effects of the ionosphere. But you can put like string waves. I mean, I have seen results there that would change that this spectrum, the 21 centimeter signal, will be sensitive to. So it's an open game. That is the best. That is one prediction, but you can switch or change the parameter, the initial conditions, and you will get a different signal.
And that would be related to the population 3 star.
Population 3 is, of course, it is. Yeah, this is supposed to be 100 solar masses stars that will only last for 1,000 years and would explode and enrich the intergalactic medium. So the next generation should be more normal. But in a very short time, it could be, we can reach good metallicity. I mean, in high metallicities, I would say.
Omar, I have a question related to to the methods to measure the supermassive black hole mass. So you show a table with different methods,
Yes.
but which one is the more confident method?
The
So
more-
because you say you did an average, but we can believe in one or other.
Yes, I think as you saw the correlation with the smallest dispersion, these are all indirect methods, right? I mean, the best one is to go and measure the velocity of stars, measure the shadow of a black hole, or go and measure the velocity of the gas and do things like that. But then you need very good resolution to enter. With the sigma, that's the one that gives us the smallest dispersion. If you measure the velocity dispersion of the stars, at least globally, up to the effective radius, you can get a good estimate. But recently, you told me, Manuel, right? That somebody said that there was a big galaxy with no black hole.
Is there anything spiral galaxy?
So as we increase the sample, things are becoming more complex because at one point, and it's not good. Well, it's sad that what is her name? One of the professors here, Deborah Dulcin, in one of these congresos nacionales said, every galaxy todas las galaxias tienen su agujerito negro. And I wrote it down, so it's a citation from her. So I would remind her. So yes, it's a
Yes, but there is a
caveat.
caveat with the estimate that we can do with the stellar velocity dispersion. So there is a breakdown to to the high mass. I mean, if you want to predict masses above 10 to the 9, this the relation with black hole mass and sigma, the stellar velocity dispersion, seems to break down. So, in fact, for Home 15A, the sigma does not predict 10 to the 10 solar masses. Instead, yes, it 10 to the 9. It has the lowest dispersion, but for instance, the one with the luminosity, the bulge or the galaxy, allows you to get 10 to the 10 solar masses black holes. So this is interesting.
Traje mi propia porra, ¿vieron? No trajiste la cámara.
¿Quiere que es la versión española y la otra en inglés.
Claro.
Maybe I misunderstood it, but you say that Holm 58, well, the flattest could be explained by three bodies.
Perhaps. Yes.
So what are the masses of these three bodies, or you cannot?
Well, the one that we measured so far, getting very close to the center of a core, is 410 to the 10. And this one that is a disturber could be about 10 to the 9 or something like that. I mean, because the extension of a flattening goes up to 18 kiloparsec. That is huge. It's a huge distance. And I wish, I mean, El Abuelo was here, right? So he could tell me about this flattening. This is really impressive. This is the velocity dispersion being flat up to the cusp radius, which is about 4 kiloparsecs. This is just so big that you need maybe a third dispersion to help you keep that thing flat all that way, right?
You cannot measure the mass directly.
Not yet. No. Unless it's clogged. They say that it has gas around, and then we can try to measure the mass of a rogue black hole that it's going somewhere around. So maybe if we find it, then we can try to measure the mass. But it has to be clogged. It means dressed, have gas about it. If it's naked, there's only the black hole there, nothing. Unless in the wake, the start wake that we will do, like a boat going into the stars, right? So if we could see the wake, then we could see and we could infer the mass. But that is asking for too much to the current technology.
Okay.
Prego.
Grazie. Sorry if the question is stupid, but how we can isolate the signal from a supermassive black hole from the background for objects that are so far? Yeah.
Well, the supermassive black hole is
Yeah.
inside the galaxy, right? And it has a redshift. So Hector already measured the signal from the galaxies behind through the distortion of the positions due to gravitational lensing. And then we can separate those because they have a higher redshift. The ones at the redshift of the galaxy, then we consider all those things that are contributing. And then what you do, you get the closest you can to the black hole in resolution. So the sphere of influence, they call it. It's not the event horizon, it's the sphere of influence, where the gravitation of a black hole dominates over the stars. And then you do the measurement there. You can, yes. So you can do that. But say if you wanted to get the purest one, you go the closest, you get the closest to the black hole, and then you measure whatever you have there. Right? Yeah, no problem.
Questions? Meantime, I have another. Please.
También trae porra.
Something related with what has been questioned before. So you say that you need 10 to the 4 mass black hole.
Initially.
How initially?
How initially a redshift 20.
Okay.
There. In order to reach, redshift 0, and all this time, allow for the mergers to happen with big major mergers to form a big black hole in a supermassive galaxy.
Can you say something between Big Bang and redshift 20 about?
Give me a theory, I will be happy. If you only give me a small pelotitas, right? I mean, what can you do? It's
the requirement.
yeah, and Vladimir is not here, so I can say it. Yeah, you give me small pelotitas. That is a phenomenological theory.
Okay. Yeah, you need that mass.
You need that mass in order to reconstruct the history of mergers and arrive to a 10 to the 10 solar masses. But theoretically, they say that there could be these 10 to the 11 solar masses black holes. Yes, exactly. You go backwards. This is reversal engineering, they call it. Well, this is done everywhere, right?
I have a question related to the sky resolution of this supermassive black hole. Do you think it's possible in the future to propose this object to observe with EHT?
Which ones? The primordial ones? The one over here? Yes, I mean, if you increase the resolution, you can get out with the event horizon, for instance. If we get more antennas and you get one further away, or you decrease the frequency, then you can increase the resolution and then you can get these ones. So if you go to less than a millimeter, which would be hard to do, then you can get it there. Or you get an antenna further away, I mean in space, then we can talk about it. That's a lot of possibilities for this. But the thing that is a message is that you can find black holes everywhere now. I mean, and wherever you look at the beginning of the universe, at the end of the universe, right in our neighborhood, there are black holes everywhere. And they might be more fundamental than we have thought, because now they are not an accident. We have better statistics and better measurements now, right? So.
Okay, thanks again to Omar.
Muchas gracias.